topics of my talk and try to make you understand something of what I have done here. Rapidly, what I said formerly was the old approach to this problem using those Eisenhardt-derived relations. But in reality, there's no real need to use those relations if you can manage the whole Einstein system. In particular, with those computer algebra methods, you can create an input file for math tensor program where the metric tensor components are obtained with this relation here. This G is the amplitude tensor, H is the perturbation tensor, and Q is the perturbating parameter. The general case where I applied this expression is the static spherically symmetric general coordinate case, with has this line element here, which is characterized by the two functions, radial functions that you solidly know, lambda and nu. The angular part is the symmetric part, normal. We obviously need to have the possibility to fine-tuning the coordinates, and those gauges are the well-known Regge-Wheeler gauges, which are divided into two groups, the axiomagnetic and the polar electric, and which reflect on the perturbation tensor, as you can see here. The polar electric are on the main diagonal, and the axiomagnetic are only those two, individuated by those coordinates I have written here. Correspondingly to this perturbation tensor, we have the perturbation Einstein part of the system, where the polar electric components give rise to this only part, and the axiomagnetic to this one. So you have a non-mixing situation. In the implementation I've used, math tensor, all the calculations of the perturbated situation are performed by adding this simple line at the end of the input file. This is a simplification, a simplifying line. Even if you are not acquainted with C instructions and so on, you can easily recognize some features of this line. And in the metric tensor perturbated, the expression in the two cases of the perturbing part is this one I have written here, where the important radial perturbing part are only represented by two functions in the axiomagnetic case and by four functions in the polar electric one. The main achievement of computer algebra calculations in this case is the possibility of factoring all the angular terms that come out from the first expression of the Einstein tensor. In particular, this simplifying procedure is characterized by those straightforwardly verified substitutions of all the angular parts you can recognize in the first expression of the tensor. The main achievement of those substitution is to give rise only to two different Legendre polynomials representing the angular parts, and this is the key feature that can perform the separation between angular and radial parts, which is the main object of this calculation. Those relations are simply derived from the application of this recurrent relation, which is well known, and by its analog of the further order. Okay, the final result in treating the radial equation you can write after the elimination of the angular parts is that you can deal with two first-order equations that depend separately on the derived functions, perturbing function you have imposed at the beginning, and so this separate dependence can be exploited to write a single equation, which is the Regge-Wheeler equation that you have here, where the tortoise coordinate r star is also employed, and this expression can be quite straightforwardly reached by those lines of programs here, where you have the solution here of the second equation, this one depending only on h1 prime, and that can be used to express h0 for further substitution in the other equation. The final result is this one. It is a quite compact equation on only the h1 variable, and where this always used substitution has been employed. This equation can be reported to this by a procedure of coefficient identification.
Obviously, for doing this, you must first write this other equation, which is a completely abstract one, that can show how this identification must be performed.
The results of these substitutions are here. You have the factor expressed in the tortoise coordinate that is expressed by this expression here, and the main result is this expression of the potential V in this generic static spherically symmetric system. This is known as the Regge-Wheeler effective potential in the Schwarzschild case. In the two cases that can be
inferred by the generic equation I have shown formerly, are easily performed by those substitutions that you know. Here you have only the two terms of the Schwarzschild coordinates, and here you must add the inverse square term. Correspondingly, you have those expressions
of each the torus coordinate and the potentials. This is the magnetic axial case. The polar electric case is quite much more complicated, and it gives rise to four first-order equations after you have performed the identification between two of the radial unknown functions. You can derive a first integral by this system of four equations. You can notice that in the Schwarzschild case you have three first-order equations and three second-order, while here you have four first-order and two second-order. So the four first-order can be sufficient to perform this derivation of a first integral, which is in fact only algebraically obtained by this by a straightforward procedure, which is this one. Obviously, when you perform only algebraic substitutions, you must take into account that you can lose some information in the differential equations you have lost, because all the other two second-order differential equations can add some pieces of information, and this is still an open problem. Okay, this is the expression of this first integral in those generic coordinates. Its analog in Schwarzschild coordinates is written in the Edelstein-Pescara article I have cited formerly. Next step is the elimination of a radial function from those system of equations, which is straightforwardly performed in this way, which is exactly the same way you use in the Schwarzschild case, as Mr. Zerilli obviously remembers. And that gives rise, by all this extremely smart procedure invented by Mr. Zerilli, to this equation here, which is the analog for the polar electric case of the Reggio-Wheeler equation, and which is called Zerilli equation, that has a different expression of the potential, obviously. So now you are left with a new system in 5 different radial unknown functions that derives from a similar procedure of coefficient identification. And this system can be still elaborated by computer algebra methods, in particular by Mathematica, in a straightforward way. The results are as follows. We have no arbitrariness in the definition of those equations, contrarily on the Schwarzschild case. We have this expression of the factor of the torus coordinate, whose integral inverse is the expression of the torus coordinate with regards to the radial one. You can check easily that this expression reduces to this one when this characteristic substitution is performed. And the only differential piece of all this reasoning is concentrated in the expression of the last radial unknown function, which satisfies a second-order differential equation that consists of 175 terms when excluded in all the monomials, the independent monomials. And correspondingly to this equation, we can write the potentials that you have here. This is the Schwarzschild potential in, I remember, the polar electric case. And this is the formal result of the Ressler-Nordström potential, which can be derived also by this generic procedure that shows obviously a more complex form, but which has those repetitions which are particular. And that's all for this argument. I can only do some little arguments involving a further argument, which is the tensor-spherical harmonics basis, always inspired to early 70s works that are inspired by the original 57 article of Reggie Wheeler and by this article by John Matthews. What you can do here is, I will summarize by voice, only to, you can achieve the calculations of the tensor basis in the two different forms of multipolar basis and of harmonic basis. Those two forms are shown by Domominacht to be linked by a combination of Clebsch-Gordon coefficients, and you have a certain amount of calculation you can do easily to verify that the expressions you calculate are right. I think this will be all, because I'm not very well. Excuse me now.
Let's give him a pick up